Here's what we're going to do. This is a definition. And here are the two examples that we're working on. So the first one, cosine t, x is equal to cosine t, y is equal to sine t. That drew the circle, and then we have x is equal to sine t, y equals cosine t, where we switch to x and y. That also drew a circle. But we saw that there was a difference of these drawings. The first one started at the point 1, 0. And although we didn't plot points, a person could possibly think about plotting points here where the input would be a t value and then the output would be a point with an x and a y that's dependent on the t. So when we have t is equal to 0, for example, that gives you your starting point. When t is equal to 0, cosine of 0 is 1 and sine of 0 is 0. So we have that starting point. And usually we just say t is equal to 0 there as a starting point if you know exactly where this point is. Otherwise, you'd actually put the point down. And then you would try another value, like pi over 4 maybe, and then you're going to get cosine of pi over 4 and sine of pi over 4. And then you get another point that you would plot. And you can keep doing this until you fill in a good significant amount of points to get a feel for how this graph will eventually look like. Like maybe, let's do one more when you get pi over 2, where the cosine of pi over 2 is 0 and the sine of pi over 2 is 1. So with these points, you can kind of tell that our graph is being drawn out in a certain way, starting from some point, and then it draws out a curve in a particular direction. Now compare that to this green graph. Where if we made that table, when t is equal to 0, sine of 0 is 0 and cosine of 0 is 1, we are starting off in a different place already. And then let me just jump to pi over 2 here, where sine of pi over 2 is 1 and cosine of pi over 2 is 0. So with 2 points, you can get an idea of where your graph is going, the direction in which it's going, and then you know where the starting point is. Okay? Now another good thing to find out is this is an image of the graph being drawn for some values of t. Now technically we should let our t go all the way from 0 to 2 pi. So if we make that distinction here, we can see that we are drawing this whole circle from 0 to 2 pi. And the same goes for this other example that we had. I had a slightly different example that we can get a chance to do, and that is an x and y combination of sines and cosines again. But this time, I think I put a 2 pi as, what's that called? Something. So if I change the period on my trig functions, where we have cosine 2 pi t and sine 2 pi t for x and y, it looks like it's going to trace out the same image that we had in the blue over here. Starting at 1, 0 and going in the counterclockwise direction. But for the t-values, what would be a good choice for putting in for t-values? Okay. All right. Good. Thanks. So it looks like it's going to draw another circle. If I put 1/4 here, 1/4 of 2 pi is what? Pi over 2. Cosine of pi over 2 is 0, and sine of pi over 2 is 1. So it looks like I'm drawing, again, the same circle. It's the same starting point as my first example, but this time I'm able to draw the whole circle, not going from 0 to 2 pi, but going from 0 to what? If I go from 0 to 1, then I'm able to draw that whole circle. Okay? So in parametric equations, when we're dealing with parametric equations, there's a lot of different variability here. The parameter, the way you set your function is going to dictate how you're going to draw your curve, how fast you're going to draw your curve, and what the image is going to look like. Okay, it would be interesting to take a look at these 3 examples and see how they would look like in your graph. So for that, let's take your graphing calculators out. And I have an 84 here, but 83 works the same way. If you have an 89, you have to figure out how that works yourself. So your calculators are defaulted to graph functions of x. Y is equal to f of x, right? When you press y equals 2, then you have y1 is equal to something with an x in it. Y2 is equal to something with an x in it. All right, so the first thing we want to do is change the mode of that. Just like you would change degrees to radians, you would change it in the same place under mode. You do probably want to stick with radians. And for the type of function you're going to be plotting, if you go to the function func, there are 4 choices here. At least in my calculator, there's 4 choices. One is parametric, one is polar, the other one's a sequence. So we're going to check out the parametric one, and in a couple of days we'll look at the polar one. So select the PAR for parametric, and then you should be good to go. When you press y equals 2, you see how it looks different already. It doesn't say y1 equals to something. It says x1t equals something, y1t equals something else. So let's type cosine. I guess you would select the cosine function. And then for the variable, you would select this xt theta n button. That provides the appropriate parameter for whatever it is, whatever function you're dealing with. For parametric equations, it's automatically going to put a t in there. If you were back at functions, it would automatically put an x in there. Okay, so I pressed that button and I got this t. So my next function for y1, I'm going to press the sine function of t. Okay. Now one more thing that would be good for you to know in terms of graphing these functions in your graphing calculator is if you move your cursor all the way to the left and you see this blinking icon over here, if you press enter several times, you'll see the icon change. So this is the default. The default is just a line. It would draw a line. The second option is to make it thicker. The third option, I think, is the one that's interesting. It has an actual drawing mechanism. It has a tracer where you get to trace your drawing. So I would opt for that one. The next one is a tracer without leaving a trace. It just tells you where the graph would be drawn, but it doesn't leave you an image. And then the last one is dotted. Okay. So like I said, I would select this tracer that leaves an image. And then the next thing I want to do is I want to go to Windows to make sure I have the appropriate boundaries. So if I like to see this drawing drawn out from 0 to 2 pi, that's not pi. Thank you. My solution for that is to lift my glasses up so I can see, but I'm trying. I'm trying not to do that. So your limits for your t-value tell you how far you want your t-parameter to go. And then the t-step should be automatically given to you, but if you're seeing that you're drawing a bunch of things that kind of look like straight lines instead of a smooth curve, the smaller the t, the better. Okay, so this is set to be 0.13. I'll leave it at that, and then you can mess around with it. Put like 1 there, and then you'll see how that'll affect your drawing. The x min and x max just provides a nice window for you. I got negative 1.3, and I don't want to go all the way to 14, so I'm going to press 1.3 positive. And then my scale just gives you tick marks along the x-axis. So if I want to scale at 0.5 so I can see that this is going to hit at my second tick mark, that's what you can do. The y min and y max are also going to be the window for your y-axis. So that's, I want to use the negative 1.3 to positive 1.3. And then the scaling again, 0.5 would probably be good. So with this, you can hit graph, and then you can see it looks like an ellipse, but that's because that's how the window is set up. And there's a way to adjust this, right? So it's really a circle. If you zoom z square, it's going to treat your window as if it was a square. So then you can actually see that it's drawn to the appropriate aspect. All right? So the reason why I like that tracer drawing for your graphing calculator is that because sometimes if I were to take this and instead of going to 2 pi, let's say I went all the way to 4 pi, that would be, well, I'll just press 4 times pi. You would see this being drawn out twice. So it finished the circle, but now it continues to draw a second path of the circle. And that'll be important for us in the future because sometimes we want this thing drawn once. Very rarely we might want it drawn more than once, but you have to know what your limits are for your t-values. Okay? So if I don't change my limits for t-values, right now I'm set up to go from 0 to 2 pi. And let's say I want to draw my other circle where I have the cosine of 2 pi t and the sine of 2 pi t. How many times do you think this is going to be drawn out? About, approximately. Without changing the window. 3 times? Oh, we have an issue there too. So what's 4 pi? This thing draws out a circle from t goes from 0 to what?
It draws a circle from 0 to 1.
This thing draws out a circle from 0 to 1. So I went from 0 to 4 pi. What's 4 pi? It's about 13 something. So this actually drew my circle 13 times. And did you notice how it was drawing it? Well, not just that, but this would be a good time to talk about the t-step. Let me change this to just go from 0 to 1 and graph. Doesn't quite look like a circle. That's because the steps that it's taking, that t-step is telling you, I start with 0. My next point I'm going to plot is going to be t is equal to 1.3. The next point I'm going to plot is 1.3 times 2. So what it's doing, what the calculator is doing, is making a table of values and then plotting it with a straight line. Now, if these tables of values are so close to each other that you can't really tell it's a straight line, then you see a nice smooth figure. But that's what the t-step does. It controls how fine you want your graph to look like. So if I want this to look like an actual circle, I would probably put 0.01 or something really small so that when I graph it, I can actually see a circle. Now, the smaller it is, the slower it might take, because it has to do the calculation for each of those points. But you get to see what you want to see. There's always a price for perfection, right? Any questions? Yes?
I noticed on the homework the t domain, or the domain for the t values, was not super explicit. Do you want us to just kind of fool around with negative t values and just try and figure out the graph?
Yeah, for homework cases, then that would probably be good to just mess around. They're not so explicit with the t values. The t values will become important for us when we need to actually parameterize these things in the future, because the way we parameterize things is going to dictate how we're going to integrate it. So we're going to integrate things over some curves. We need to know how did you draw the curve? Did you go from 0 to 2 pi, or did you go from 0 to 1? And then based on that, those are going to be the limits of your integration. Okay? All right. So some of these things can't go onto our static notes. So our class will have video notes and static notes. These static notes would be a PDF of everything that you're seeing on this whiteboard that I have. But unfortunately, I can't make this static. I could take pictures of it and put it on the computer for you, but that's not going to be the same as seeing it kind of done in action. That's going to be useless. But whenever I can, I'll put things statically, but you'll always have a link to the YouTube video. Lisa?
Can you put a screenshot on the button?
Maybe in the future. So I did a lot of messing around here. If you can decipher that, that would be great. So now it's in our notes. All right. So any questions about these circles? So I try to make a big deal about circles because they are kind of a big deal for us. But let's try to examine other types of graphs, graphs that you might see in the homework, and then graphs that will be important for us later on. Some of the exercises that you guys have in your homework assignment asks you to take a look at, see how the graph might look like, and then sketch the graph. And then they also want you to combine those parametric equations and eliminate the parameter. I think that's a fun exercise and all, but that's not going to be useful down the road. So I think for the sake of doing the homework, you should know how to do it, and I'll do one or two examples. But in the future, I think it's more important to get an understanding of being able to draw out these things. So let's pick a problem here. You guys want to pick one? Pick one. 6. Let's do number 6. So we have x and the t value. X is equal to 1 minus 2t, and y is equal to 1/2 t minus 1. And they give us specific limits for the t, going from -2 to 4. So what we can do, for starters, is to plot points, right? Or what I would do, I'd just punch it in the calculator, see how it looked like. But let's plot points for the meantime before we punch it in our calculators. And this will give us some idea of how this is going to be drawn as well. So our t values go from -2 to 4, and I think this is good enough to pick whole numbers. I see a 1/2 here, so I might just go even numbers at that. So -2, 0, 2, and 4. And I'll skip all the odd numbers for now. If you really need to, you might need to put in the odd numbers to see how it might look like. When t is equal to -2, my first point will be at, let's see, -3, comma, -1, -2.
-2.
So 0 is a nice easy one. When t is equal to 0, I'm at 1, comma, -1. When t is equal to 2, I am now here at -4, so 1 minus.
Wait, I think we did the first one wrong. It should be positive 3, -2.
For serious? Really? You guys are checking my work, right? Because I make a lot of mistakes on class, in class, in lectures. Some on purpose. Okay, when t is equal to 2, where am I at? 0, comma.
Oh, sorry, the first one was -3.
-3, comma, 0. And are we tired of this? This is really, really hard, huh? Oh, we're just getting the wrong numbers. Oh. When t is equal to 4, where are we?
-7.
One? All right. Well, with this information, we should be able to plot points and then draw a graph and see how this thing would look like.
For -2, should +5?
I don't know. I'm just writing. I'm just writing stuff down.
It's positive. It's so wrong.
This one?
Yeah. Hey, that's like twice removed from I stopped saying things.
Say again. +5? All right. So if we were to draw this, we got 1, 2, 3, 4, 5, -2. So this is our first point, and you can label it with actual point 5 comma -2, or for me, I'll just label it as t is equal to -2 because that's the t value that gives me that point. 1, -1, when t is equal to 0, we have 3, -3 comma 0, and then we have -7 comma 1, and we see that this kind of draws a straight line. So in this particular situation, we have a graph of a line, not just a line, but a line segment. Now we don't bring this to go out in positive, negative, infinity, because they actually gave us limits for our t. And so because of those limits for t, we're restricted to this particular line segment. And then we also know that this is going in a specific direction. T is equal to -2. You start from lesser to greater, -2, 0, 2, and t is equal to 4. So this is a line. Okay? And it turns out that if you have linear functions for x and t, then your result will be a linear graph, a line.
You always go from lesser to greater?
You always go from lesser to greater when you're doing things. So even in this case, it's going from right to left. We need to go draw our arrows from lesser to greater. So it's important to go from lesser to greater. Question?
Are we using the dots and the holes for the endpoints?
We won't use holes. A lot of times these things will include the endpoints, and so we'll just sometimes they overlap. Like in our circle example, we started at 0, we started at 1, 0, we ended at 1, 0. So both those points are technically on the graph. If we want to be really meticulous about that, we would take away one of these equal signs or something like that if we need to be. A lot of times overlapping at one point is not that big of a deal. All right, any questions? Now the other thing they want us to do is to eliminate the parameter to find the Cartesian equation for the curve. So what we could do is we could take a look at this. We have x is equal to 1 minus 2t, y is equal to 1/2 t minus 1. To eliminate the parameter, you simply set them equal to each other. What does that mean? Solve for t for 1 or both, and then set them equal to each other that way. So let's see. Solve for t. For the first one, we got x minus 1 divided by -2. That's your t expression. If you go ahead and put that into the y is equal to 1/2 t. What was t equal to? X minus 1 over -2. And then you can leave it like that or simplify it. I don't know if the homework system would allow you to leave it like that without simplifying, but I would say that that's correct. Yeah?
I encountered a problem with one of them where you had to take a square root in order to solve for t, and it didn't like the plus or minus. I don't know how to deal with the plus or minus.
And maybe you might need to get t alone in the other equation.
Oh, really? Just choose one?
Yeah. So this is...
Sorry, but I know which problem you're talking about. When I tried to do it the other way, it didn't accept that as an answer. So the answer was like, y is
So do you only choose like one, because you said that parametric equations that have to be functions, so do you just choose a positive or a negative, or how does that work?
Well, you could choose a positive and negative depending on how the graph looks like.
Okay.
And you can make your decision that way.
Okay.
All right. Any questions about this? Now, some of those other, this is an easy one. This is a linear function. Even the number 8 is a cubic function, but it's still something to do with cubic functions, and it's still easy to deal with. But if we take a look at our very first example, where we had x equals cosine t, y equals sine t, or any of those other examples that we've dealt with, the idea of eliminating a parameter here is a little bit less intuitive. And what they just expect you to do is they expect you to know some trig and be able to work with some trig functions. Okay? What they want you to look ahead to is that trig identity, the cosine squared plus the sine squared is equal to 1. So if you can get to that idea, well, what if I square this? I square this second one, and I add them, I should get this thing to equal to 1. So if I add these two things, I would have this added together would be cosine squared t plus sine squared t is equal to 1. But your idea is to eliminate the parameter, right? So you take a look at the other side. Oh, that's x squared plus y squared is equal to 1. So that is your image in Cartesian coordinates of this particular parametric set of parametric equations. Now, whether you had 2 pi here or whether you had the sine and cosine switched, you'd still have the same image. So that's the same thought process or same idea where you have different parametric equations drawing the same graph, the same parametric curve. So this also can get simplified to a sine squared plus cosine squared. As long as the angle is the same, you're going to get x squared plus y squared is equal to 1. It's going to draw out the same circle, except it's going to draw it slightly differently. It's going to draw it differently. Okay? And then there are other things that you can't get into a Cartesian coordinate relation, or you would need a lot more trig than what we're required to know. Not required, expected, what I'm expecting you to know. The trig that I'm expecting you to know is really on the surface level. And if there's some other trig identities that we don't really have to know for this class, but I would expect you to be able to look it up if you needed to. All right, any questions? So eliminating a variable for linear functions is pretty easy. Even for some polynomials, it's easy enough to do. And when it starts to involve trig, think about your very important sine squared plus cosine squared identity. Okay. What else? Oh, I had some other interesting. Oops, went too far. Some other interesting graphs that we should probably take a look at and be able to graph. It says do not use a graphing device. We can use graphing devices. Oh, it says match. We don't have what it's matching to. So let's find out how these things look like. Well, now that you know how to do this in your graphing calculator, you should be okay about just plotting these things. Let's do a couple of them in the graphing calculator. And see how they might look like, and see how we can adjust our graphing calculator windows and parameters and stuff so that it would actually fit these graphs. Let's do the first one. We have a polynomial, a 4th degree polynomial. So let's have t to the 4th minus t plus 1. And then we have just a t squared. And right now, I think my graph goes from 0 to 1. So let's graph this to see how it might look like. All right. So it graphed too slow for me, so I need to change my t-step. Maybe instead of 0.01, 0.1 would probably do. And then I got this little bit of a graph over here. That went from 0 to 1. So I might be interested to see how this graph might look like for t that's negative, because it might draw something a little bit different. So let's go ahead and into the window and adjust the t min to be maybe -1, maybe even -2. And let's go all the way up to 2 in this case. And then because I want it to draw a little faster, let's do 0.1 for the t-step. And we could be happy with the window that we're in, or it looks like this is being drawn in the first quadrant, so I might change that later on. For now, let's just leave it where it is, and then let's graph it again. Okay, so it looks like I might be out of my range here, so maybe I do want to stick with the first quadrant, and I do want to go beyond 1.3 or whatever it was I had earlier. So I'm going to go back to the t window and specify that I want to go from 0 to, let's go to 5 for now, and then the y min at 0 and the y max at 5. All right, so it looks like this. Now the graph in the book where you do the multiple choice thing doesn't look like this, so it's some other window adjustments that you might need to do if you need to figure out what these things might look like. Okay, but for now this is what I have. I'll go with this. Any questions? Well, let's see. Let's leave it like that. All right. Let's do the one with a sign and sign inside of a sign function. So let's go ahead and change our functions. Sine 2t. And then the other one is a weird one, sine of t plus the sine of 2t. So by the way, you can get this set up to zoom to a particular area, or zoom standard gives you a -10 by 10 or 10 by 10, 20 by 20 window. So you can hit zoom standard, or you can do a zoom fit, I think. Where's the zoom fit? A zoom fit kind of estimates where your graphs would be, so that might be another way to possibly start trying to figure out how to set up your windows. Looks like Zorro. Okay. And I think for this one, we went from -2 to 2 for your t values, but if we go from -2 to say to 4 or something like that, we might see more of this. Okay? So that's generally how this particular graph would look like. Any questions? Combinations of trig functions, sine and cosine functions with different periods also make nice graphs. Let's take a look at D. Let's take a look at D. So let's go to the y equals 2, and we have sine, or we have cosine, sorry. Cosine of 5t, and then for the next one we have sine of 2t. And then we go to, let's just go from 0 to 2 pi for this one, for t values. And let's go ahead and graph it. Oh, I didn't adjust the windows, but this is one of those cool drawings where it draws a nice curvy, wavy shape. And then if you go further than 2 pi, say go from 0 to 4 pi, you'll see that it's going to draw the exact same image beyond 2 pi. So that's another cool drawing. Have you guys ever played with a Spirograph? So that's a cool way to try to express parametric equations using spirographs. It's combinations of circles within circles. We'll study a little bit later on. We'll take a look at the path that the Earth takes around the Sun, and then we'll take a look at the path that the Moon takes around the Earth, and then we'll see how the path of the Moon is compared to the Sun if the Sun was in the middle. It's going to be, we can express all that with parametric equations, and if we assign a time frame to each of those things, we can actually imagine when exactly we will have our eclipses, or lunar and solar eclipses and things like that. And also, did you know that there's an asteroid that's come really close to the Earth? So that's being tracked by a path. The asteroid is apparently well known. I think it's AB86 or something like that. It's a cool name for an asteroid. Anyways, that asteroid has a specific path that it's taking, and then the Earth has its own path that's being tracked by NASA, and so they're figuring out how close those things are. So those are all good. Hey, those are all good exam problems, huh? So we'll see. You need binoculars.
Yeah.
At least, yeah. All right. Now, once we know a little bit about these parametric equations, since we are in a calculus class, we should do some calculus on these parametric equations. And we'll start by doing calculus that we know, finding regular derivatives. So in this section, we're going to try to find tangent lines, and then if we have time, we'll find areas within some curves and find arc lengths as well. If you remember your calculus, we know that the derivative is equivalent to the tangent line, kind of loosely speaking. More precisely, the derivative at a particular point gives us the slope of the tangent line at that particular point. So it really comes down to actual values. So in other words, if you're looking for a tangent line to some curve, say your curve was f of x, and you're looking for the tangent line here, what you would need to do is you would need to take the derivative and not only take the derivative, but actually put in the actual point. So df dx evaluated at your a value, whatever that x value is for that point. And that will give you the slope of that line. And now that you have the slope, you just put it in the point slope form, or if you remember your Taylor series, it's the linear form for the Taylor series. F of a plus f prime of a times x minus a. Yeah. Oh, that. So the actual equation of the tangent line, if you were to look at this as in point slope form, we have a comma f of a. That's the point, and we know the slope. By the point slope formula, we can say y minus y1 is equal to the slope times x minus x1. And then if you bring the f of a over to the other side, this is essentially your first order Taylor polynomial. So that's how you would find your equation of the line. Remember that? Okay, so whether you remember Taylor polynomials or not doesn't matter, as long as you can find equations of lines, which I hope you know how to do, if you have a point and a slope. That's really what we need here, is a point and a slope. So imagine now, instead of a function y is equal to f of x like we have here, if we have a parametric function, x of t, y of t. So we have a parametric set of equations that describes this point, and at some point over here, when t is equal to a, we're at some value, then we should also be able to find the equation of the line. And what do we need for an equation of the line? We need a point and a slope. We have the point when t is equal to a. What's my point over here? Can you describe my point based on my no. What? X of a is your x value, and y of a is your y value. So that's your point. So the only thing that's left to do is find our slope. And our slope, if you have a set of parametric equations, our slope will be given by the derivative of the y with respect to t divided by the derivative of your x with respect to t. Which looks pretty natural as a dy dx value, right? It looks like the dt's would cancel, but we don't want to think about it that way. Let's just think about this as a formula where you have y prime of t divided by x prime of t. So our slope is going to be given by y prime of t divided by x prime of t. But remember that t is just a parameter. When you take the derivative, you get a function of t. You want to actually evaluate it at that point. So here is the evaluation marker that says I want to replace t with whatever it is that I'm looking at, in this case, a. So let's see if we could do an example after I write the equation. And all it is doing a bunch of derivatives, doing two derivatives, one for the x and one for the y, and then putting in the values, whatever value you're given. So this is formally our formula for the line, but I don't, it's not something that I would want you to memorize. It's just something that I want you to be able to come up with by just using the point and the slope business. So let's take a problem from a graph that we did previous over here. Let's take this first one, a. That's x t to the fourth minus t plus 1. So let's do an example. Our x is t to the fourth plus t or minus t? Minus t plus 1. And our y is equal to t squared. And let's find let's find the derivative at not the derivative. Let's find an equation at a tangent line at t is equal to 2. So the slope, remember, is one of the main things that's the calculus part of this problem, is taking the derivative of the x and then the y. So the slope is going to be y prime of t over x prime of t, and then we're going to evaluate it at t is equal to 2. So let's go ahead and take the derivatives of x and y. The derivative of y is 2t. The derivative of x is 3t squared minus 1. So let's go ahead and put 2 in there. 4t cubed minus 1. All right, let's go ahead and put 2 in there. We have 4 divided by something big, 8, 31. So 4 over 31 is your slope. Now we also need xy points, right? So we'll put t is equal to 2 in for x. Now I need 2 to the fourth power. That's just 16 minus 2, 14 plus 1, 15. So that's 15. And the y is 4. So you have your point, you have your slope, and you just come up with the equation of the line. So y minus y1 is equal to the slope times x minus x1. And that's all you need.
So when we're doing this, you don't want to specify that for the reminder that we're over?
For me, I don't care. If you're putting it into your computer, they might be a little bit more specific. But to me, this is an equation of a line, so I'm happy with this. Unless they say you have to write it in form y equals mx plus b. Any questions? So it looks like my x value went all the way to 15, which in my graph I only went up to 5 or something like that. So if we want to get a better view of this, I would extend my x value to 15. In fact, I'm kind of interested in graphing the graph again on my graphing calculator along with this line. So we're going to come up with an interesting problem that maybe you guys can think of how to solve. But I want to graph both of those graphs. So I'm going to go ahead and type that first graph again, which is t to the 4th. And then t squared. And then I'll adjust my window this time to get my t values. I think I went from -2 to 4 or something, or -2 to 2. But if I let my x-min go from 0 to something that includes 15, like 16, I can be sure to account for that point when t is equal to 2. And then my y, I think that could just go from 0 to, it didn't go past 5, so I'm going to try 4 this time. Maybe I want to go, let me adjust my window again. Go all the way up to 20 for the x max, and then the y max. I put it down to 4. I think I want to go back up to 5. So if I trace this, when t is equal to 0, if I'm tracing it and then I type 0, it gives me my t value and tells me where I am exactly. And so I'm interested in finding out where I am when t is equal to 2. And that's going to give me 15 for my x and 4 for my y, which is what I had anticipated, right? So now I want to graph this line on here. This line is a y equals f of x business. How am I going to graph that line? Any ideas? You got to turn this line into a parametric equation. So the parametric equation has x and y values as functions of t. This is clearly not in parametric equation form. But it looks like if we solve for y, it can be written as y equals f of x, right? So I guess that's the question. How can I change y equals f of x as a function back in the function mode in my calculator and change that into a parametric equation if I'm interested in graphing it parametrically? Any ideas? Yeah?
Can we just plug that into one of our original functions that we were given? So if we have t squared is equal to y, and for y is equal to, we just take square root of
Not quite. So the exercise that we had earlier was to eliminate the parameter and write it in Cartesian form. Now, we are in Cartesian form. What I want you to do is come up with a parameter and write this in parametric form. Did they do that in the book?
Wait,
No, they didn't.
Can you use partial fractions?
No?
I don't know.
All right. So I'll tell you. T was your independent variable. That's your parameter, right? And you put that as your independent variable. So if you have y equals f of x, you already have a built-in independent variable x. So why not let x equal to t? What does that mean? That means for every value of t, you're going to have that value of x. And when you put that into your y function, now you have a y value that's also run by the parameter t. It used to be run by the variable x, but now you're just replacing x with t, and it's still going to draw the same graph. So it's going to draw the same graph, except now you have a t for your parameter, and x is equal to 2. Okay? So if you were to try to plug that in your graphing calculator, now you have an x and a y to plug in, your x being t, and your y being whatever it was. Instead of an x, you put a t in there. So it's 4. Whoops. So it's 4 plus 4 over 31 times t minus 15 . And so now if you graph that, you graph oops. What happened? So I need to get my t going all the way up to 15. So 15 or 16 or 20. I'll tell you more about that later. But here's your graph of the original function being drawn out. And then
Just going to 20.
our step is small. Well, you get the point. All right. So there's a couple of other objectives that we didn't get through here in this particular section. Let me go ahead and trace this real quick. There it goes. So a couple of other objectives, like other calculus, like taking integrals. So we need to find areas under or between parametric curves, and we need to find arc length. Okay, so we'll talk a little bit about those and then move on to the next section. All right, see you guys tomorrow. If you want your quizzes, it's on the table.